In this video for lesson 6C.4, we're going to look at vectors and parametric equations, and that's the new word, parametric equations. Hopefully we can relate our idea of vectors from before to this to make it a little bit easier to understand. And it will make it so we can kind of go through the process. So first, we're going to answer what is a parametric equation. And we can use the mathematical definition. It's used for modeling movements of objects moving in a straight line. Each value of time will establish an XY ordered pair. Or we can think about it like common sense. And so let's think about it like I am throwing a ball up in the air. And so here I am, there's the ball, and I am going to throw it up in the air. Now if I ask you, what does this dashed line represent? You're going to tell me it's the path of the projectile, and you're right. And if I ask you, okay, well, what are the variables of that path? You might say, well, it's a horizontal distance. How far away is that ball from you? Which is my x, or it's the vertical distance, how high is the ball in the air? And you're right, there are, you would think, two variables. But there's actually a third variable. And that third variable is how long is the ball in the air? The third variable is time. So there's really three things I can talk about when I'm throwing an object in the air. I can look at how far away it is from me horizontally, I can look at how high it is vertically, and I can look at how long is that projectile in the air. And that's what parametric equations do. It gives us an ability to figure out, if I know here is the ball, and I know how long that ball has been in the air, and so I say, hey, you know what, the ball has been in the air for 1.5 seconds. I can create an equation that will allow me to find what's my horizontal distance by knowing that time, and what's my vertical distance for knowing that time. So parametric equations uses time to find the position both horizontally and vertically of a projectile. That's a very basic understanding of it, and hopefully that clarifies what we're going to be working with and why these equations are going to be unique. But to start, we're going to find a way to relate it back to vector equations. And so when we did vector equations for it, and I don't need this right here. So when we do vector equations, we're going to think of it back to how we did in the class was the standard form, x2 minus x1, y2 minus y1, we considered it kind of like slope. Hey, this is my run, and this is my rise. Makes sense. So what a vector equation is, and I'm going to try and be consistent with this, is I'm going to make vector equation green, and we'll do this on the problems, the examples on the bottom as well. I'll use that same color. Is it finds the equation, the vector equation that is parallel to what's given to you. And it has to go through the given point. And the idea is I know a point, I know the vector, I just don't know what the scale and how long is it in the air, what's the scale of it. So I'm going to use the same type of formula for a vector equation. I'm going to find a way to just plug it in the way we're used to. So notice when we're dealing with this, we're going to have the same idea. We're going to subtract x's to get our run, we're going to subtract y's to get our rise, and we're going to have time times this. So we're going to come back to that. The next part is a parametric equation. And again, to be consistent, let's use blue, and I'll use blue on the bottom for this as well. So parametric equation, if I look at it, I can see right away something very interesting. It's really parametric equations. It's plural. Notice that parametric equations are two equations. And I addressed that in the beginning with the throwing of the ball is there's a horizontal and there's a vertical. There's an x and a y we want to find. And so that's really what these two are. Is your parametric equations are going to be based off of that. Now, parametric equations, what they allow us to do is they allow us to write a linear equation with respect to time. And that's going to come back into play a little bit later on what that means. But we can look at a projectile and think about it as two equations. What's its horizontal position and what's its vertical position? So we're going to first start with, and I used green, we're going to start with writing a vector equation. And the vector equation is going to use the given information. I know what the original point is. So here's my vector equation. I know it's going to go through 1, 4. I know that. And I know it's going to follow this, I say slope, this path, this vector. I just don't know for how long. I don't know for how much time it's going to do that. What's the scale of that vector? Who knows? So when you're writing the vector equation, you know one of the points. You just don't know the other point. You don't know where it's ending. You know where it's starting. You just don't know where it ends. So my vector equation is x2, which I don't know, minus x1, y2, which I don't know, minus y1. That would be my run and my rise for my slope. That is equal to, I know it's going to follow this vector, 3, -2, but I don't know for how long. And so if I scroll out and kind of look, all we did was we followed this green formula. x2 minus x1, y2 minus y1. I just don't know what those values are, so I'm going to leave them as x and y. My time, right here, don't know what the scale is, so I'm going to leave it as t, times the given vector. So that's your vector equation. That's it. We can use that to create, and I used blue, let's go to the highlighter, I used blue to write the parametric equation. And so that's going to be the work that we're going to have to do a little bit more. Not too complicated, but we're going to use this and we're going to create our parametric. And the way we're going to do that is we're going to first distribute the right side. So I'm going to leave this alone. There's nothing to do with this. But on the right side, I can take that scalar of t, time, and distribute it in. And what I can do at this point is I can set corresponding parts equal. I can set the x's equal to the x's. I can set the y's equal to the y's. So I could say x minus 1 equals 3t. I could say y minus 4 equals -2t. And then solve. So I would add 1 and go 1 plus 3t. I would add 4 and get 4 minus 2t. And notice for parametric, our constant comes first. It's not the idea of mx plus b. It's your constant and then your time variable. And also notice it's a pair. There's one equation for the horizontal and there's one equation for the vertical. That is the parametric equations for this. We can take our vector equation, distribute the time, and then set the corresponding parts equal to each other to solve. So same idea for number 2. Is the first thing I'm going to do is I'm going to do the vector equation. Now I'm just going to use the colors instead of looking at the highlighter. So my vector equation, I know its position as a coordinate. I know its rise and run that it needs to follow. Run of 6, rise of -3. I just don't know where is it going to end. And I don't know for how long is it going to follow that path of 6, -3. So I'm going to do x minus a -2, so x plus 2, y minus 4 equals my 6, -3 vector. I just don't know for how long what that time is. That is your vector equation. I'm going to create my parametric equation by first distributing the t on the right hand side. So 6t comma -3t. And then I'm going to set my corresponding parts equal to each other. And that's going to create my parametric. I would say x plus 2 equals 6t. I would say y minus 4 equals -3t. So x equals -2 plus 6t. Y equals 4 minus 3t. And there are your parametric equations. 2 equations, one for the horizontal and one for the vertical. So that's how we can create a vector equation and how we can use that equation to create a parametric, and we're dealing with it. It's an understanding to kind of relate. The green relates back to 6.3. We just don't know, as I said, what the position of it is. I know what shape it should follow. I say the word shape, but what slope it should follow. And so I can create this from that. And then from there, I can create the parametric. Parametric are a pair of equations. So we're going to have one for x and one for y. So that's the first part of the lesson. Please make sure when you're doing these problems in the homework, you read the directions and make sure if you understand if it's asking for you to write the vector equation and the parametric equation on them. Now the back side is a little bit different. So here what we're doing is we are converting, and I'm going to take some time and have some fun with this on trying to explain it, is we're converting linear equations. So let's just kind of write down the most basic linear equation we know, y equals mx plus b. And let's count. That is one equation. Simple. We are trying to convert that to a parametric equation. Now that's a little bit harder because a parametric equation is x equals something with time and y equals something with time. Well, we'll count those. That's 2 equations. So we're trying to take one equation and we're trying to create 2 equations. One that says x equals something with time on the right hand side, and one that says y equals something with time on the right hand side. So the way it works, the way you do these problems, if you're going from one equation to 2 equations, is, well, you have to create a new equation. You have one. Good news is I have one equation. I don't like the variable x here. That bothers me because I want parametric, and parametrics need to be t. So I at least know I have one. I need to create the other. So to create the first equation, so what you do is you first set x equal to t. Create that for second equation you need. I'm going to say, you know what? X equals t. Done. There is one of my 2 equations. So I got one equation. Boom. Now let's create that second one. Y equals, well, I already have an equation that says y equals, so let's follow that. Y equals -4, good. X, well, I don't like x, but we just said x equals t, so -4t plus 7. That's it. That is how you convert a linear to a parametric. So really, we just set x equal to t, and then we use the given y equation to write the other one, replacing the x with t. So one thing to keep in mind is that linear equations, the x is the independent variable, and the y is the dependent variable. Your value of y depends on what you plug in for x. You know, this is your input, this is your output. But for parametric, it's a little bit different. For parametric, t is your independent. Your time is your independent. X and y are both the dependent variables. So when you're dealing with this, you need to realize you're going to have 2 equations for parametrics. One for the x and one for the y. But the way you create your 2 equations is by first creating the equation x equals t. That takes care of one of the equations. And then I can use the template, the structure of the other one, y equals 1/2, but for parametric, I need to use time. So x equals t, so 1/2 t plus 7. And that's how you convert from linear to parametric. I gotta tell you though, that's the easier of them. Sorry. But let's apply the same logic to make the harder ones a little bit more interesting and not so hard. And that's going from parametric, so let's think about that the way we did above. Going from 2 equations to slope-intercept form, which is really linear, which is one equation. So we're trying to analyze how to go from two equations, one that says x equals something involving t and one that says y equals something involving t, to one equation, which was linear, which is something with mx plus b, y equals mx plus b. So really, if I look at that right-hand side, there is no time on that right-hand side. You get rid of that variable time when dealing with linear. And I know these both share that variable time, so that has to be the key. So if I look at this one, right equation, slope-intercept form, what I'm going to do is I'm going to take these two equations and I will try and kind of color code the steps for you. I'll have x equals -5 plus 4t. And over here, y equals 2 minus 3t. I'll just write them horizontally. I see that they both share, and we'll do an orange, they both share time. They have that variable in common. So what I'm going to do is I'm going to solve for time in both equations. And so I'm going to add the 5, and I'm going to divide by the 4. And I'm not going to do anything tricky with it. I'm not going to write it as a fraction with like the 1/4 x plus 5/4. I'm not going slope-intercept form. I'm leaving x plus 5 divided by 4. And we'll see why in the next part. So I'm going to solve for time here. I'm going to subtract the 2, and I'm going to divide by the -3. And again, I'm not going to do -1/3 y plus 2/3. I'm just going to write it like this, and we'll see why in the next step. So by doing that, by taking what they have in common, they both share the y, and solving for it, I can now do the next part. I can find a way to get rid of that t. Since they both are now t equals, we can set them equal to each other. And I mean, think about that. I have two equations. Like, still, I have two equations there. That's not plus sign, it's supposed to be an and sign. I have two equations. I want one. But since they're both solved for t, I can set them equal to each other. I can say x plus 5 over 4 equals y minus 2 over -3. And that is just brilliant because now my two equations are one equation. We're there. We have one equation like we're supposed to. And that equation only has x's and y's, which linear form only has x's and y's. So to solve, I'm going to cross multiply. And that's why I left them in this form, is it allows me to cross multiply pretty fast on this. Equals 4 times y minus 2. So -3x minus 15 equals 4y minus 8. And just keep going, slope-intercept form. So -3x minus 7 equals 4y. And I get y equals -3/4 x. Now I'm going slope-intercept form because it asks it to. There's your answer. We are done. I took a parametric equation involving x and y, and I changed it into a linear equation. And that's it. How did I do that? Is I took what they had in common, which is my time. I solved for it in both equations. That allowed me to merge them together into one equation like I'm supposed to have with just my x's and y's and no more time, and I could solve for y. So to me, thinking logically about it kind of makes sense. Two equations to one equation. So we do that by seeing what do they have in common. And they have a t in common. So I'll kind of follow the same color coding. So the first thing I'm going to do is I'm going to solve for t in both equations. And I'm not going to make it too complicated. So x plus 2 equals t. If I want to put over 1 so I can think cross multiplication, I can. You don't have to. Subtract the 4. And then divide by the -3. Again, not going to look at it as -1/3 y plus 4/3. I'm just going to leave it like this. And because they both are solved for t, I can now set them equal to each other. I could say x plus 2 over 1 equals y minus 4 over negative 3, and my two equations become 1 with just x's and y's, no more t, which means I can go into linear form. And I can do that by going back and thinking cross multiplication. 1 times anything is just itself, so I'm going to leave that as is. So negative 3x minus 6 equals y minus 4. Slope-intercept form, negative 3x minus 2. There it is, my final answer. So I hope if we look at these two together, it's the idea of how many equations do you have to how many equations you want to go to. And hopefully that helps you understand the thought process between linear to parametric, this part, and parametric to linear, that part. Now, I need you to get your calculators out, and I'm going to just pull up the completed notes for this part, since I don't have the TI-84 app on this, and you can kind of look at how we're doing this. So if I look at the completed notes on what we're dealing with, so 6C.4, and here we are, make sure on your calculator you hit the mode button and go to parametric on it. So for the mode button, it's up on the top of the calculator, and you want to make sure when you hit mode, it says function, either para or par, polar or pole, and sequence, and it's the second one, para, under mode. And when you do that and you hit your y equals button now, you should have on your y equals, when you do this step, you should have your screen saying, hey, x1, I think there's a little t there, and then it says y1, a little t there. And you're able to type these two equations in on, and I could type negative 5 plus 4, but don't hit and find that t button. You want to use your variable button, the x, t, theta, n, and this is really what your modes are: function, parametric, polar, and sequences. So you want to hit that button. Don't hit alpha, t, it's not going to work. So for this one, I'm going to do 2 minus 3, and then I'm going to hit that x variable button. Same thing here. And what I want you to notice when you do that in your calculator is the calculator, the graph, has a starting point. I'm going to use red. It has a starting point right here, and it has a direction it goes. And that's what you need to notice for your table. Your table is going to start at 0 because time is 0. That's the smallest time you can have. So it's not, when you graph these, they're not going to go full-blown linear all the way over to the left, a line. It's going to be a ray, just like our vectors were. It's going to have a starting point based off of time being 0. And you can just type in your calculator and plot the points. Now, like I said, I don't have the calculator app on this, so for me, I want to have some fun. And I want to know how to do this without the calculator, and that's the interesting part, knowing how the calculator works. And so if I look at this, and I think about it for a minute, we know we have to start here because time is 0. That makes sense. So I'm going to look at what that coordinate is. Negative 5, 2. That's that first starting point that I plotted. Well, that's interesting because if I look up above, that's right here. Negative 5, 2. That's kind of like your y-intercept. You think slope-intercept form, the constant is your starting point on the y-axis. Maybe the constants are the starting point for our parametrics. Well, let's check it out in number 8. So if I look at number 8, there's my starting point right here. And my constants are 3, 1. And yep, that is my starting point, 3, 1. So that is very interesting, that the constants of your parametric give you the starting point of your ray. Well, that's helpful, I guess, but you got to figure out, well, how do I know what direction I go? Where do I draw the rest of my ray? And it's a really good question, but here's the other part. There's another part to the parametric equations. This. And if I look at my graph, 1, 2, 3, 4, I have a run of 4. I have a rise of negative 3. So let's see, 1, 2, 3, 4. And I'm going down negative 3. Let's see, 1, 2, 3, 4, and I'm going down negative 3. So this is my run, and this is my rise. Wow, it's just a guess. Let's check the next one, see if it works. So in this case, I would have a run of 2 and a rise of 1. So let's see. I'm going to the right 2, up 1, right 2, up 1, right 2, up 1. Yep. So we don't even need the calculators if you don't want to. If you want to have fun like I do and you want to do it by hand, this actually tells you how to do it. The equation gives you everything you need. You have your constants as your starting point, and you have these coefficients of the variables acting just like slope does in slope-intercept form. Your y is your rise, your x is your run. So I think that's awesome. Hopefully you understand parametrics and your calculators can go through it. If not, learn how to do it by hand. But that is the introduction to parametric equations.